This video is sponsored by CuriosityStream. Get access to my streaming video service, Nebula, when you sign up for CuriosityStream using the link in the description. They say nothing travels faster than light, and yet virtually all of the universe is moving away from us faster than light can travel, out at the edge of the universe. So today we are continuing our Faster Than Light series by traveling all the way out to the edge of our universe, and also asking what we mean by edge and how many edges we might actually have. As a fairly notorious skeptic about ever harnessing faster than light travel, beating entropy, or making perpetual motion machines, I find it a bit ironic how often I have to tell folks about the big glaring exceptions to these concepts, and the physical laws that make them apparently impossible. The first law of thermodynamics tells us energy is neither created nor destroyed, that it merely changes in type, with that energy being fundamentally conserved. But energy is not conserved, not in all cases. And we have known that for over a century now, nearly as long as we know the laws of thermodynamics. It is implicit in the Big Bang cosmology that our universe began at some point, with lower entropy than now, and with the same energy as now where none was before. We can say maybe it came from somewhere else, as is sometimes suggested for dark energy, but that just kicks the can down the road and is logically flawed for thermodynamics. Under thermodynamics, entropy is only foreordained to eternally increase in a system if it is a closed system, and the moment you say maybe that matter or energy came from somewhere else, or a prior iteration of the universe, you just said maybe the system is not closed, which is fine. Again, it just kicks the can down the road to assuming something beyond our universe, and we're not bothered by kicking cans down the road in science so long as the can arrives where it's supposed to be, which for a lot of theories is apparently a recycling center. So today I want to discuss why physicists don't seem reluctant to tell folks energy is conserved, entropy always increases, and the speed of light cannot be exceeded, when in reality energy is not conserved, entropy does not always increase, and most of the matter in the universe is moving faster than light relative to most observers. Welcome to Science and Futurism with Isaac Arthur, where we just go ahead, grab our paradoxes by the horns, and embrace them. Alright, let's start by discussing how we currently believe the universe works versus what we thought back when the laws of thermodynamics were getting set in stone. The current interpretation of the Big Bang Theory by most folks is that the universe used to be a single point, or erupted from such a point, and expanded to its current size and continues to expand. This is not quite correct, but it gets the basic bit right. The universe appears to be expanding in all directions, and from this we assume it used to be smaller. There is no evidence for or against it being point-like at the beginning, incidentally. That's just a reasonable deduction from the fact that it gets smaller and smaller the further back in time we look, as far back as we can look. Folks often wonder what's outside the universe, or what it is expanding into, and what we would find if we flew out past the edge. I've heard a lot of people answer back that the universe expands into nothing at all, or that the universe has no edge. It's possible that either might actually be the case, but there's no evidence for or against, and there are many other options. With no offense to any cosmologists out there, there's obviously been tons of speculation and modeling of how our universe is laid out and where it came from, or how it might not have needed to come from anywhere at all. But while the popular media often gushes about this or that theory, there's not much supporting them, even the nicest of models, and it's resulted in a lot of folks being very assertive about how the universe isn't expanding into anything at all. We do not know that. We just know that it doesn't seem to be expanding into anything else, and that speaking as though it was an explosion widening out implies it's just the matter of the universe expanding into a big empty space. That's not what the Big Bang was. It was the expansion of space-time itself, and the space actually stretching out, not matter expanding into some existing empty space from some sort of big explosion. I have heard a lot of analogies offered, usually involving balloons, to illustrate how we are stretching space. But the one I've come to favor is just to imagine that you are making a map of some fantasy world or dream home or garden or whatever on a computer. If you decide to make it larger by changing the map scale, your fantasy home or garden hasn't actually expanded into anything. At the same time though, it did, in that it expanded on your hard drive. If the map went from 1000 by 1000 pixels and you sized it to 2000 by 2000, the notion of what it expanded into and how it expanded gets a bit abstract. That's the key thing about the universe expanding. We don't know that it isn't expanding into anything. We just know that it is not expanding into existing empty space. How it does this and why, we do not know. And indeed, the computer analogy might be right on the nose. Again though, this does not mean it actually expanded into nothing. Indeed, some of the Big Bang variants I have heard of include that the universe is vastly older and bigger, and just had Big Bangs erupted in it occasionally. We also do not know that it was not infinite from the moment of the Big Bang either. We just know our bit of space-time stretched out from something smaller, and we can only see back to when the universe was around 370,000 years old, but it was pretty tiny back then, the bit we can see anyway, though still bigger than a modern galaxy. The further you look out, the more redshifted the light from those objects is, meaning the faster they are traveling away. This is linear too, double the distance, double the speed they are moving away from us, and you need not factor in any relativistic Lorentz equation for speed. It is not like approaching the light speed limit on matter or a ship speeding up, where each new burst of energy has less effect on the total speed as you approach light speed ever closer. It is just the product of new bits of space popping up or stretching or whatever the heck it does. Whatever the heck it is, it appears to happen everywhere at roughly the same rate, so double your distance, double the speed the object moves away in totally non-Einsteinian terms. At a certain distance, it is 60% of light speed. At twice that distance, it is 120%. Honestly, I think this confuses a lot of folks because they expect it to be more weird to calculate. At the 100% marker, no photon of light or graviton of gravity can leave an object and ever reach us, or us them, to be seen or affected. No event can be witnessed, and most of our universe we can see now is actually past that point, what we call the cosmological event horizon. This is one edge to our universe, but more in a practical and metaphorical way. We cannot ever see beyond that or travel beyond it, making it a practical edge. If this were the edge of our universe, not only would it be constantly expanding in distance as the universe expands and ages, but also violate conservation of energy in the sense of all that matter, all those galaxies near the edge, constantly flying over it to reduce the amount of mass and energy in it. Of course, it might be getting replaced by dark energy, but the key bit there is that we keep the notion of conservation of energy by simply tacking on that it is locally conserved. In any given chunk of it, the various interactions will all add up to zero, except where matter is entering or exiting that chunk, or temporarily popping in and out from quantum events. The tricky part is that since space keeps expanding, something does not have to be at that 100% light speed distance to be invisible to us in the future or its local or current present. The space is stretching, getting added to, or subtracted from, the speed of light coming from that distant object and heading our way. Determining that distance where an object right now can no longer send a signal we would hear, even though we can see it currently, albeit in its state billions of years ago, is harder to calculate, but this is that event horizon. We just can't see events going on there anymore, and this includes the supermajority of the observable universe, most of which we see as it was before Earth even existed. Now inside this bubble, entropy is increasing, though dark energy is a bit harder to factor in too, since we know very little about it except it is apparently spread out evenly everywhere, and so it's probably not doing anything to decrease entropy. It's a big question mark there since we know so little, and indeed one theory for dark energy I have heard is that it contributes to why time runs forward. Inside the finite observable universe we can measure, and for those elements we can measure inside it, the amount of entropy rises, and I should note that only in a finite object can we really say entropy rises. Start talking about something infinite in size or time, and things get a little more tricky in metaphysical terms. Incidentally, the pre-Big Bang model most scientists subscribed to in the 19th century and early 20th century, when the laws of thermodynamics were getting locked down, was an infinite Newtonian one. Space always had been, and always would be, and was infinite in all directions, hence why it did not collapse on itself from gravity. This does not work, but it should be noted that in any finite system, given long enough, entropy as a concept resets. Shuffle a deck of cards enough times and the order it was in will repeat, since there's a finite number of orders it can be in. Expand this notion out to any closed system and you would get the same result, and also same for non-closed systems like a region of space bound by neighbors that were essentially the same sort of thing. Like if folks see a table with each other, each with their own deck of cards, occasionally flicked one to their neighbor or grabbed one from their neighbor. A reset still occurs eventually for each player, but also for that whole table too. I want to emphasize that because while the edge of our universe in terms of where we can see is a decent enough place to just dub the edge of the universe, it is not really valid across the board, especially if we're talking about the sum total of all things. Ironically, it does have certain correctness in practical and metaphorical terms since again, under current known science, It is the sum of all things we can ever detect or interact with. Now, this raises the notion of other types of edges, like up and down, in the sense of higher dimensions and such, for a given value of higher dimensions. Now, we can hypothesize a place where there's a fourth physical dimension at a right angle to up and down, left and right, forward and back, but string theory and some other cosmology suggest we need not look to other universes to find these. Without digging into string theory or any of its many derivatives, versions, and cousins, let us imagine that back at the Big Bang it was not actually point-like but more binary. There was a single left position, a single right, a single up and down and forward and back, not a dot but a cube 2 by 2 by 2, where everything in reality could be in one of 8 possible states, and which for some reason then expanded to be a kajillion by a kajillion by a kajillion. Let us assume it actually had more than 3 dimensions though, not all of which behave quite the same, which we know to be true in the sense that it had a time dimension, or maybe gained one from the expansion moment. Let us assume there were some dimensions that had an up or down state that did not expand at the Big Bang. Conceptually, think of a sheet of paper. It's not really point-like in terms of depth, it has an upside and a downside, and making it thicker or thinner does not change that, and sheets stacked above or below it do not change that either. In this case, those sheets would be parallel universes. In this example, you would have 2 physical dimensions that were expanded and one that was not, and a direct application of 3D physics to such a 2+1 universe would require what we call compactification, as that one thin dimension is compactified. So light particles, for instance, which expand in our universe in all 3 dimensions, and thus fall off with the inverse square of distance, would in a compactified paper-thin universe fall off only inversely with distance, a tenth the strength at 10 times the distance, rather than a tenth squared or a hundredth the strength as it does in our universe. Key to string theory, M theory, and some variants is that we have 6 of these compactified physical dimensions, so it would be a 3 plus 6 physical universe, in the same way our paper was 2 plus 1. This does not necessarily mean the compactified dimension has only 2 states, it can have just one or several but less than others. But often that up and down or positive and negative is assumed. 10, 11, and 26 dimensions are popular suggestions for totals, rather than our normally assumed 3 physical and 1 temporal dimension. It is also often assumed these smaller dimensions are ring-like, a tiny little circle. These compactified dimensions, regardless of their specific characteristics, are assumed to be much smaller than even an atomic nucleus, indeed probably smaller to them than they are to our planet. We may do a video on string theory someday, but not today. And we are interested in those extra dimensions because much like a sheet of paper and a stack of them, if we can imagine there's some right angle to reality that our universe is just a single layer or sheet in, then it implies the possibility if you could pop up or down this hyperspace onto another sheet. Hyperspace is a pretty vague term in science fiction, but in math a hyperspace is one with more dimensions than our own, same as we would be to that sheet of paper. In this context, you wouldn't be jumping a spaceship into hyperspace, you would be moving from your universe, or sheet of paper, up or down in hyperspace to a neighboring sheet. You and that sheet already exist in that same hyperspace, same as 2 pages in a book do. You are traveling in hyperspace, but it isn't meant to imply some separate place you jump into, as we often see in science fiction. How you would do this, I have no clue. How does a letter move from one page to the next? I suppose if we were stretching the paper analogy, we might argue that everything in our universe occupies either the up or downside of that sheet, and might share its upside with the higher level's downside, so if you could flip all your states being only the up or only the downside, you might be able to get a toehold on the sheet above or below. That's a conceptual way you might move between layers of reality, but keep in mind, it is assuming those compactified dimensions have up and down sibling levels. That's an assumption not too dissimilar to the one about what our universe is expanding into with the normal Big Bang. Nonetheless, in terms of hypothetical fast and light travel methods, that is the basis for hyperspace in the context of places congruent to each other. That sheet of paper is really 3-dimensional and has a time component too, so the sheet above or below, or at various other right angles, since we're not just assuming 4 physical ones either, could be universes where time has passed less, younger ones, which were smaller but which you could return from having covered more distance in our universe. Sort of like jumping backward in time to travel in our younger and smaller universe, then jump back to now having covered a vast distance, but without the temporal paradoxes. To play with that notion, a ship jumping from our universe into a congruent younger one probably would not want to move to any more compact than our own period of last scattering, the epoch of the universe about 370,000 years after the Big Bang, where it finally widened and cooled enough that the universe was no longer as hot and dense as our sun's own photosphere, which would not seem a very safe place to be moving a spaceship. But the portion of the universe we observed wasn't nearly 100 billion light years across back then, as it is now. It was more like 100 million light years across. So a ship able to leap into such a congruent universe and move around there would be moving about 1,000 times faster in terms of distance covered when it leapt back to our universe. That younger universe at that time would look like a sun's surface, which in addition to being quite hot would also be providing an awful lot of drag forces when you try to move through it. But one might imagine it would be a net benefit, especially if you had something like a walking Bussard ramjet pushing your ship, fueling yourself off that hot gas all around it. Needless to say, you could jump back even further to a congruent universe even younger, but you can't plausibly jump into the inflationary epoch, for instance, since not only was the whole universe about a millimeter across then, but it only lasted for a tiny fraction of a second, and would be hotter than inside a star's core. So moving a spaceship there that was more than a millimeter across would be a dubious concept anyway. For anyone feeling like writing that up as their sci-fi settings method of FTL, your speed amplification there is basically going at the redshift or Z of that universe, and presumably folks base their shift on how much their ship and engines are going to let them glide through in terms of denser and hotter younger universes. It would raise the question though of not just how you were jumping between universes, but also why you bothered coming back, since colonizing younger universes has a lot going for it, albeit not one so young and hot that entering them kills you. Maybe as a hand wave you can only jump to expanding but dead universes. For those curious, you can calculate the CMB temperature of the universe, in terms of redshift or vice versa, as the temperature in Kelvin being 2.73 Kelvin times 1 plus Z. So the bathwater epoch, about 10 to 15 million years after the Big Bang, where its temperature was comparable to a bathtub, would be when Z, redshift, would end at around 100, equaling the freezing temperature of water in Kelvin of 273, so that the universe was about 100th its current width and decently smaller at the warmer earlier start of that epoch. I can't think of any obvious reason you would travel through older congruent universes or migrate there, maybe to hide in a place few would visit. Anyway, that's one type of hyperspace, and also one way to think of the edge of our universe, or arguably to think of that hyperspace as the true universe containing many leaves, sheets, brains, or whichever that were like our universe. The thing is, this is still talking about universes with the same characteristics as our own, though we should note that this is not a mini-world style multiverse, any more than our observable universe is a mini-world style of galaxies. Mini-worlds is all of the what-if timelines version. This is just a bunch of different universes which share the same physical laws and have the same congruency. Time travel incidentally would be an example of traveling in hyperspace, and the fact that we only move through it, but at a set rate and direction, gives some hope that if other dimensions exist, motion through them might be possible. I should also probably note that we do not travel through time at a set rate universally. Time really does run slower where mass and energy are compacted, like on planets or near galactic cores or of course near a black hole. That is another event horizon type of universe edge incidentally. We use the term event horizon so much these days that I think the meaning gets lost. The horizon is how far you can see, though if you move toward it or away from it, you will never have the horizon itself actually get closer or further, though it would if you went up or down. An event horizon is where two objects can have actions occur to either one of them, which can be witnessed or impact the other. As a simple example, once you fall through a black hole's event horizon, you can send a message home to your planet to ask folks to do things. It's just they will never get that message. They will never observe the event of you sending it or in any way be altered by your effort. This is another of those metaphorical edges of the universe which is also arguably literal too. We do wonder if once inside a black hole you are effectively in a new and different universe, passing through a gateway into one or maybe even creating one. If that's the case, it's something we can presumably add more to from above, but not leave from below. A one-way gate you can enter but never return through. Variations on this concept are a popular one for explaining where the Big Bang came from and maybe even where dark energy comes from, but beyond being speculative, it is also a good chance to explain that no, we are not living inside a black hole. That sometimes gets suggested since the radius of a black hole is linear to its mass, and when the universe was younger it certainly would have qualified as a black hole by a simple calculation of mass and radius in the Schwarzschild radius of black hole event horizons, but this is a bit meaningless since the usual assumption is there isn't anything outside trying to look in at us, and who would not be able to see us as a result. If there were, presumably stuff on the fringe would be falling in, and rather we expand and have stuff fly over our cosmological horizon. Also, while the interior solution for a black hole resembles a closed, finite universe, the bulk of current evidence says that's not what we live in. Still, it's a decent option that black holes might germinate new universes, and we might be in one such. I'd mentioned earlier that we don't even know that our Big Bang wasn't infinite to begin with, just that the bit we can see is finite and was smaller some time before. Nothing says an infinite thing can't expand. So too, as we discussed with multi-dimensions where some expanded and others did not, things could be infinite in our usual 3 dimensions, but not in other physical dimensions or in time, and thus these might have edges. To use our planet as an example, its surface has no edge, and you can walk around it infinitely, but you can arguably go upward to infinity despite there being an apparent limit of the sky. Nor should we assume we only have one temporal dimension, or that there aren't other dimensions besides space or time. Same as those living on a sheet of paper wouldn't know what the depth of it is. If some other non-spatial or temporal dimension exists, but we only get that infinitely thin slice of them, either because they are super thin or we can only experience a thin slice of them in our chunk of reality, these can be other edges of the universe. So the edge of the universe might be thought of as billions of light years away, but in many ways or in many models it might be so near at hand that our best instruments are incapable of measuring the tiny distances involved, or so far away that we might never step beyond it, at least until we discover how to walk at right angles to reality. I mentioned earlier that we might do an episode on string theory one day, but if you want to find out more about it without waiting on me, Curious Minds has an excellent 2-episode look at string theory over on Curiosity Stream. Also, while producing the episode, which is essentially our FTL series episode on hyperspace, I felt we didn't look at all the implications to the Fermi paradox, the big question of where all the aliens are, and it's also a topic I forgot to cover in our Fermi paradox multiverse episode a few months back. So we'll take a few minutes to discuss that as an extended edition of today's episode over on Nebula. Interesting feedback loop there too. I write the episode scripts months in advance but make the video a week or 2 out, and there's almost always some topic I think I'd wished I'd discussed more in the episode, so we do the extended edition, and half the time I write those I want to expand them into full episodes of their own later on. If you didn't know, Nebula is our streaming service full of awesome content from STEM creators like Real Engineering, Mustard, Answers with Joe, MKBHD, Renee Ritchie, and a bunch of others. It's designed to give creators more freedom than other platforms, and our episodes of the show appear early and ad-free on Nebula, and we have some extended editions too, as well as some Nebula exclusives like our Coexistence with Aliens series. Now you can subscribe to Nebula all by itself, but we've also partnered up with Curiosity Stream, the home of thousands of great educational videos, to offer Nebula for free as a bonus if you sign up for Curiosity Stream using a link in our episode description. That lets you see content like Curious Minds String Theory, and watch all the other amazing content on Curiosity Stream, and also all the great content over on Nebula from myself and many others. And you can get all of that for less than $15 by using a link in the episode's description. Incidentally, I mentioned earlier that some theories about gravity and time and entropy and dark energy try to link them all up to explain why time, unlike the 3 physical dimensions, seems to have one direction, and there is a great discussion of that by Matt O'Dowd, the Era of Time and How to Reverse It, over on PBS Space-Time, and he is one of the very few folks I know who can explain deeper aspects of cosmology in simple and intuitive terms. Alright, that was our last episode for the month, but we're still not done with August, as we have our monthly livestream Q&A this Sunday, August 29th at 4 p.m. Eastern Time. Then we'll leap right into September with a look at the future of thorium on September 2nd, and human-machine teaming on September 9th, and our mid-month Sci-Fi Sunday episode on stealth spaceships on September 12th. Then we'll celebrate the 7th anniversary of our original episode on megastructures with a look at megastructure death on September 16th. If you want alerts when those and other episodes come out, make sure to subscribe to the channel. And if you'd like to help support future episodes, you can donate to us on Patreon or our website, isaacarthur.net, which I'll link in the episode description below, along with all of our various social media forums where you can get updates and chat with others about the concepts in the episodes and many other futuristic ideas. Until next time, thanks for watching and have a great week.